Hi, I'm Don Berchoff, CEO of True Weather Solutions, a weather data analytics company that transitions and takes complex weather data and turns it into simple insights. I myself have 35 years in the weather business. I started in the United States Air Force and have built big regional weather centers, ran Air Force bases, and I have also actually done some flying myself. I was the National Weather Service Science and Technology Director for 4 years. And what I've done is we've created a company here that is going to unleash the power of science and technology that is in our nation's labs and universities, bring it into our production and make it available to the economy. Today, I'm going to talk to you a little bit about our focus on smart cities and what we see as the vision for how to bring proper infrastructure for weather and weather services to this industry. So I'm going to share my screen with you now. True Weather is excited to be in South America and in the country of Colombia. We're very proud of what we've done in the weather industry to date, and we're looking forward to working with Skyscraper and all the companies and industries that are trying to bring the UAM infrastructure to life. As we all know, weather impacts all our decisions. True Weather has been very involved in UTM, Unmanned Aerial System Traffic Management Service Suppliers. We've been involved in AAM, Advanced Air Mobility, with NASA. And we're actually helping to develop some of the constructs around weather services as we go into the future to help in this complex ecosystem. We also are running the ASTM F38 Weather Group, which is looking at specifications for new weather standards, where we're looking at moving away from certifying instruments to certifying data. And that way we can lower the cost of weather measurements so that we can crowdsource them and use them to fill in gaps and help to get the micro-weather climates needed depicted in order for safe and productive UAM operations. Our focus on autonomy really comes down to knowing that there will be no, obviously, pilot controlling the aircraft. So you lose the heuristics of that pilot when you remove the pilot, which means that your systems and your analytics have to be better and sharper, and they have to carry some of those heuristics with them into your algorithms. We look at the problem of microweather data as one that's solvable if we focus on crowdsourcing weather data from different types of data sources, as well as running analytics that does validation and calibration of that data to make sure it meets a certain standard of performance, and then turning that data into mission impact decision support tools that help folks make decisions. And it's also going to be important for us to take advantage of edge computing technology, processing on the edge, and even running some of these analytics and detect and avoid services through weather at the edge to turn them around quickly in real time to help keep people safe and keep the airframes safe. So our approach really starts with sensors and crowdsourcing the best sensors. We actually have a group of sensor providers we work with, and these sensors aren't going to be all the traditional weather sensors you see at an airport like an ASOS. We're going to be looking at different types of sensing technologies that are going to fill these gaps. And then it's running those sensors and the data sets through analytics that helps prepare the situational awareness framework that we run our models and also run our machine learning models to help in the predictive side. So you're going to have the real-time concerns of knowing where weather is changing dynamically, but then you're also going to have the predictive side, because what we've learned in the last couple of years is that when it comes to urban air mobility, especially in congested cities, you have to have predictability in your journey. And so in some places like New York City and Los Angeles, you're going to have to make the go, no-go decision up to 5 hours in advance, because you can't have a change in mode for a client if they have to get to the airport and it takes them 2 hours to get there by car. So these are the things that True Weather is thinking about as we build our weather services. It's not just about the data, it's also about the operations, the workflows, and building targeted payloads that we can deliver for the right application and the right decision that's being made. And then we integrate those into the decision systems, the command and control systems, the ground control systems, the air traffic management systems through the UTMs, so that we can make better decisions. The smart city sensor and ecosystem, including, this is even for any UTM, really in weather, it's an ecosystem that starts with collecting data. The biggest limitation we have in prediction accuracy is data. And the reason why we're not wholly accurate as much as people would like is because even the current atmosphere is an estimate of what it really is, because we don't have enough data to measure it. So we do a lot of assumptions. The more data we can bring into the system, the less those assumptions, and then those run our models, and then errors do propagate through that. And so if we have a bad initial condition assumption, we're going to see those errors propagate. If we have a better initial condition with better sensors, we're going to see those errors minimized a little bit. There are still obviously challenges in science, and there's a lot of estimate that goes on to prediction. But the bottom line is that True Weather's focus on improving the data so we can improve the outputs and the predictions through a very systematic approach. So when we look at Colombia, we know we're focusing on 3 areas right now, Cartagena, Bogota, and Cali. So we actually did a deep dive into some of these areas to demonstrate for you what's possible in the weather business. Most of this would not even be recognizable to you what's possible, because if you're using just government data sets or apps, you're going to just get the standard data sets they make available, which aren't really tuned or honed for this industry whatsoever. And so what I'm hoping to demonstrate today is that this industry is going to require a change in the weather business model for aviation. And we need to figure out how to do that. We need to figure out how to fund it. It's not going to be the governments that can pay for this. And we're going to have to figure out how to implement it and integrate it, right? So looking at the main routes that you've been looking at in these areas, what I loved about Colombia is the difference in the terrain. And each of these locations have a different terrain footprint that makes weather forecasting fun and challenging. Cartagena, being on the coast, is a windier location than the other 2 locations. And with any kind of buildings and obstructions, those winds are going to get accelerated through Ventura effects. So we also have the effects of cloud, probably, and fog and things like that we have to worry about. What you're looking at here is we've ran 2 models. These are our models. We've taken the global model, which is about 13-kilometer resolution, which means the weather looks the same in each 13-kilometer box. Imagine that. And what we've done is we downscaled it to 1-kilometer resolution so we can pick up the terrain influences of the wind. And what you see here also is we ran this at 10 meters, which is near the surface, and also at 80 meters, at about 250 feet above the surface. And what I wanted to show you here is that this is just a typical day in Cartagena, and the winds at the surface were running in the 3 to 5 knot area. So when folks go out and they use the measurements on the ground and they go, okay, I've got my measurement from my forecast, what's really happening is they don't really know what's going on aloft. And this was an interesting day because we picked up a string of 10 to 14 knot winds. Now you might say, okay, Don, this is not really that relevant. It's only 10 to 14 knots. We can still operate. And that's true. But what's important to know is that your battery power and the weight that you're going to carry could be affected by what the winds are doing aloft. If they're 3 times stronger and they're not a tailwind, which in this case it's more of a crosswind, it could be a problem, right? And then if these winds change, we need to be on top of that for that reason. You also could get inversions, which can cause turbulence if these winds increase too quickly with height. And that's something we need to understand if we want to worry about client comfort and passenger comfort. So what we did was we took those winds and we overlaid them and integrated them into that flight route that you had for your that was given to us. And what we did was we showed that we used a wind risk profile where the winds greater than 10 knots aloft would depict a risk zone, right? Now most customers can pick what they want as their thresholds in our system. So we picked this just so we can depict it. But in general, if you're worried about winds of 20 knots or 30 knots, these will get picked up, and you'll at least know what the risks are. And these are meant to be really quick decision tools to help make decisions. You can optimize this route if you are worried about weight and battery power. And this program we have, which is our Routecast, will allow you to run an optimized route. It'll pick up a better depiction of where you should fly this to help save battery power. If you look at Cali, it's in the valley between two mountain ranges. And this was a boring, I have to say, weather event for us. So I ran through it anyway, just to, depict for you, just to show you what, what transpired here. And so, this is our route risk profile, and it was green, which means the winds were light. They were very light throughout this whole situation. And so in this case here, Cali, would have been really a no issue day. I'm sorry about that. Why is my screen doing that? Okay, go to Bogota. Bogota, I really love Bogota because you have the big hills to the east of Bogota, and the elevation up at 7,000 feet. So we looked at, which means we have to worry a little bit about density altitude if the temperatures get too hot up there, and that would be something we would track. We would have to keep track of, and that would help inform, passenger weight and things like that, and fuel. But what we did was I really found this fascinating because in Bogota, we ran the model again and we had 10-meter winds. And, what I found was this convergence zone right along the mountains at the surface. If you look at this, the winds are coming in from the east, the west, and then they're coming in directly east, and you have this convergence zone. So imagine if you wanted to fly, you had an air taxi route that was taking people up into the hills because maybe they lived on the other side, and they wanted to come in and work in Bogota. Having an understanding of this, which probably wouldn't be picked up on a global model, is important because you're going to see what's going to happen. You're going to go in this case, you go from a tail to a headwind. And then also the wind increase with height, the speed has increased it pretty significantly up to 80 meters. So again, just understanding this environment and how it's going to impact your operations is really important. The other thing I found really interesting about this, well, let me first run you the route cast. Again, no problem if you're running along the route that was depicted for this presentation. It's all green. But then we decided to look at a route that maybe you wanted to go into the hills. And the elevation's about 2,000 feet higher, I guess. And what was interesting is you started seeing how the winds picked up and you got that yellow impacts through these areas. Again, these weather days were not significant winds. The things that we're really going to worry about in Bogota are showers and thunderstorms. But if you wanted to optimize your route, again, here's a case of our tool helping you to optimize that route. But what I really found interesting at Bogota was that mountain ridge, right? So if you look at the surface at 10 meters, you have convergence here. This line that I put in here is going to represent the surface convergent line at all. I'm leaving it the same place at each location. And notice how when you increase with height, that convergent line moves further to the east. So up to 1,200 feet, that convergent line has moved. It's moved several kilometers eastward. And again, this is just interesting if you're, again, trying to fly in an area where an occurrence like this could happen. Understanding that's going to be really important for a lot of reasons. There could even be a little turbulence in this area when you're flying through it because you're getting the shear due to the directional change along the hills. And these are the kinds of things that, we can bring to Colombia. And I think the main point of all this is to demonstrate to you that we have the ability to basically go anywhere and to look at these situations and build solutions for any particular area that in the world. This is an image of Colombia's radar, and I just wanted to show you that we have access to it. The reason I wanted to show you this is, again, this is going to be probably one of the issues that we're going to deal with in Colombia is the rain and the showers. Not to say you can't fly in rain, but it will be impacting at times, especially if you get in heavier showers and thunderstorms. And this is going to be a challenge for that 5-hour predictability, I'm thinking. So it's going to require a little bit of effort to work through this and to help improve some of the forecasting that's going to be associated with that. Now, just to kind of get into the picture of how do we solve this problem, in these areas of the world, we're looking at the city and the landscapes and the urban environments as being significant, because the winds that come through those areas are going to pick up, and placement of vertiports, placement of routes. Are those routes going to be static or dynamic? Do we want to have an ability to have more than one route that we can have as a backup or secondary routes if the winds are, behaving a certain way, if those thunderstorms are going to be behaving a certain way? And you don't want to impact predictability of the client flying. So these are all the things that I think about when I'm, trying to merge weather with operations. And so, we're going to be looking at, right now we have a NASA SBIR where we're actually optimizing, looking at CFD modeling, computational fluid dynamic modeling, and trying to figure out where the sensors have to be in locations. Where do we optimize placement of weather sensors? What kind of weather sensors do we want to use? And, also assist in placement of vertiports so that you're not putting them in a place that's going to be weather disruptive. And there's ways to do that with climatology and things like that. We have sensor providers right now. We have 5 of them that I'm working with. And what I consider these is the blend of sensors that are going to be required to close the gaps in what I call the weather data dead zone, which runs from about the surface to 3,000 feet. We don't have a lot of measurements there. Satellite data works up down to about 3,000 feet. Maybe once in a while we'll get some good readings below that, but it does attenuate as it gets closer to the ground. So you have to fill it with ground-based and profiling-based capabilities. And so when I think of the ecosystem for this, I think the cities, I think of something like the Anna Moment, sonic wind device that would be placed in the city areas. I think of something like the IntelSense sensor, which is much less expensive than an ASOS, and it's been tested by the Air Force and used by the U.S. Air Force in deployed environments overseas, and they land airplanes with it. So it may not be FAA certified, but it's definitely a quality instrument. I think about wind LiDAR sensors, maybe on roofs of buildings that have scanning capability. So like in a place like Cartagena, where the winds may be a little stronger, this could help us collect better wind information. Or if you had them in a place like along the ridge of the mountain, it would help us understand what's going on. You don't have to put these everywhere. It could be a targeted observation network that just fills in the gaps for the things you need in order to get a better picture of what's going on. You also have drones that are weather instrumented drones that can be flying as weather scouts on days where you're uncertain about things. And then you have traffic camera analytics, which we use in the US today. We can take weather data off a camera and change that into visibility and precipitation data. So what we did is we ran an urban CFD model over Bogota to see how the winds would behave in a very specific area around Bogota with the buildings and get the effects of the buildings, because weather models can't pick those up by themselves. And this is an example of the day of all those models we ran to show you the winds. This is the same day, and we took those wind models and downscaled them with a computational fluid dynamic model to show you what the wind flows would look like in urban areas around Bogota. And this was a light wind day, so it's, this is exaggerated a little bit, but I think the main point here is that you can have your average wind speed at 1 to 2 knots, and you can expect winds in some areas to be up to 3 times faster in areas where you have Ventura effects. So these green areas represent areas where the winds are picking up going through the buildings. You also have to worry about wake turbulence coming off the buildings and how that's going to impact landing at different vertiports. And this was the worst day of worst wind direction, worst wind that you've ever had in Bogota. We just ran the computational fluid dynamics on it. And here's an example, again, the wind's coming from a different direction, and how you could see how those winds are, the stronger winds you have to watch out for in these areas, because these winds coming in, the green, are the average winds that the model that would blow on a day without a city building in the way. And then look what those winds, what happens as you begin to get into areas where the winds can become 2-3 times stronger. And we want to keep people out of those areas. So what we do is we can use our route optimization software and things of that nature. This is an example of just what we're looking at in terms of the 5G network and tying infrastructure and weather instruments into existing smart city infrastructure, right? So we run on the backbone of this infrastructure, and our sensors collect the data, and then we bring it back to the cloud, or we run it locally on these platforms and then turn back around the information locally to increase the time, to reduce the time to get that data back to the decision maker. And we do have a plan for 2023. All this is going to come together. We're working on building a scalable, computational fluid dynamic service offering along with the sensors to go and stamp them out city by city and have a consistent approach to where the sensors will be placed, how to run the models, and providing, decision support that would be provided to UTMs, unmanned aerial system traffic managers, a FIMS network, if that's what Columbia decides, or an AAM user. So that's what I have for today, and I hope you enjoyed that and learned a lot about what weather can do for you and do for the autonomous industry. Thank you.